Did you know humpback whales inspired a revolution in wind turbine design when we learned from their pectoral flippers? You're listening to Wild Engineers, decoding nature's intelligent designs in your coffee break. Let's dive in. Wind turbine efficiency, which refers to how effectively a turbine converts kinetic energy from wind into electricity, can be significantly reduced by environmental factors, mechanical wear, and operational errors. Leading-edge erosion, gearbox failures, and poor positioning within a wind farm can drop production as well. Hi, I'm Melanie Farmer, and today's question is, how does nature maintain stable, efficient flow in dynamic conditions? Meet the humpback whale, Megaptera novae anglii. Despite weighing tens of tons, these impressive marine mammals can turn sharply while swimming at speed through highly unpredictable waters. Biologist and Professor Frank Fish, I know, best name ever for the topic, noticed something unusual. Their flippers break a rule engineers have followed for decades. Instead of smooth leading edges, humpback flippers are lined with rounded bumps called tubercles. At first glance, they look like drag-inducing defects, but these structures shape how water moves across the flipper as conditions change. Hydrodynamic testing revealed what the tubercles are doing. Each tubercle generates a small controlled vortex. Together, these vortices keep flow attached across more of the surface, even as angles of attack increase. The effect is that drag decreases, lift remains available for longer, and flow transitions become controllable. In essence, those bumpy pectoral fins distribute pressure into smaller, manageable regions. A company appropriately called Whale Power translated this design directly into their wind turbine blades. They figured air and water are both fluids, so the design insight should be transferable. When tubercle geometry was applied to their rotating blades, testing showed increased annual energy production, improved performance at lower flow velocities, reduced noise under turbulent conditions, greater operational stability, and strong durability under storms, ice, and unsteady flow. In essence, consistent performance was achieved by designing surfaces that remain effective across a wide operating envelope. We started by asking, how does nature maintain stable, efficient flow in dynamic conditions? Nature's strategy, embodied by the humpback whale, is distributed flow control. The mechanism includes structuring the leading edge with bumps to create vortices, installing separation channels between those bumps, enabling more manageable flow attachment in variable conditions. So, if a flow system performs well only under narrow conditions, it carries hidden risk. But whales invite us to consider that stability might be achieved when we distribute impact along bumpy rather than smooth surfaces. That's wild engineering. Thanks for listening, stay wild, and see you next time. That's it for this episode of Wild Engineers. If you're inspired to apply nature's intelligence in your own work, check the show notes for more detail. If you know someone who could benefit from this episode, please share and help us redesign our world inspired by nature.